Okay, now we're going to take a look at organic nomenclature. So the ability to be able to name organic compounds is really important in terms of discussing organic chemistry. And what we need is a way to name a compound so that when we provide someone else that name, they can draw out exactly what the structure of that compound is with no ambiguity. So the rules around naming compounds are quite complex. There's a lot of variety possible amongst organic structures. And so there's a lot of rules that are often hotly debated. And those rules are set in place by the International Union for Pure and Applied Chemistry, or IUPAC. So we'll just go through the most important parts of those rules so that we can have a common language about how to talk about compounds. So in general, organic compounds are named using a three-part naming system. Firstly, there's a prefix, and that's normally a number or a type or a position of substituents on the backbone of a particular compound. Then there's the parent, so how many carbons are there in the longest chain within a alkane? So, and then the naming gets a little bit different if it's not an alkane we're talking about, if it's a cyclic system, but we'll just concentrate on alkanes for now. And then finally a suffix, and this really tells us what is the functional group upon which we're basing the name of this compound on. So if it's an alcohol, we'll always end with ol, saying it's an alcohol. So here's an example of a compound here, 4-bromo-7-methyl-oct-1-ene. So that is a compound that we could name using the rules I'm about to go through. So the IUPAC rules for naming alkanes start off with selecting the longest continuous chain of carbon atoms in the parent compound. So that's the first step. Then you number the carbons in the parent carbon chain starting from the end that's closest to the first carbon that has an alkyl or other substituent. Then you name the alkyl group and designate the position of the parent carbon chain by a number. When you've got the same alkyl group on the chain and it occurs more than once, then we use a prefix to say how many times it occurs. So di for twice, tri for 3 times, and so on. And when there's several different alkyl groups attached to the parent compound, we list them in alphabetical order. And this doesn't just apply to alkyl groups, it could be other groups like halogens, bromo comes before chloro, and so on. Okay, so naming alkanes, there are some common groups and how they're named. So methane obviously is the simplest alkane, and then a 1-carbon alkyl group attached to some other chain is named a methyl group. Then the 2-carbon hydrocarbon is ethane, so a 2-carbon substituent on another molecule is called an ethyl group. But then we have things like the propyl group and so on, and butyl. Now, we can get to situations where we have not just a simple linear or unbranched alkyl group, but we have a branched alkyl group, and we need to distinguish that from an unbranched alkyl group. So an isopropyl group, if we draw that as a Kekulé or line bond structure, then we're going to have a group that is attached through a carbon atom, then that carbon atom has 2 methyl groups attached to it. So that's an isopropyl group. We can have isobutyl groups. So this is where we have the branching like that. So we have a 4-carbon chain where there's branching one further away from the position by which the group is attached to our main chain. A sec-butyl group, on the other hand, is where we have the branching point is on the carbon that's directly attached to the main chain. And then tertiary butyl group is where we have the 3 methyl groups are all attached to that 1 carbon atom. So all of those, isobutyl, sec-butyl, and tert-butyl, are all 4-carbon substituents joined in a different way, varying around how the branching is happening. Okay, so let's go through some examples, because the rules are really quite dry, and I think it really becomes clear once you talk about examples. So here we've got a branched alkane. So firstly, we need to find what is the parent alkane. So what is the largest continuous chain of carbons? It's a 5-carbon chain, so it's a pentane. Now we find what is attached to that, and we've just got the 1 alkyl group, and in this case it's a methyl group, so it's a methylpentane. And then we number the chain according to, And then we number the chain, starting with 1 being a position that is closest to where that substituent is attached. So we start numbering 1 at this end and go towards 5 at the other end. So the methyl group is attached to the 2 position, so this molecule is 2-methylpentane. Okay, so here's a couple more examples. We've got 2 branched alkanes here. The first one and the second one, they're both butanes, so that's the longest chain. Then we've got 2 methyl substituents, so they're dimethylbutanes. And then we number them so that we start numbering closest to the substituent. So the first example, it doesn't matter which end we start from because it's symmetrical. But the second one, we need to start from the right-hand end so that we get 2,2-dimethylbutane rather than numbering it from the other end when we'd have 3,3-dimethylbutane. Okay, here's a more complicated example. So what's the longest chain here? We've got a 7-carbon chain, so there's going to be a heptane. And then we're going to number it so that the substituents get the lowest possible numbers. So there's more substituents at the right-hand side. So we start at the 1 position and go towards the left. And we end up with 2, 3, 4, 6 tetramethylheptane in this case. Okay, now where many people get tricked up is that we draw the molecules in a certain way and then we change how we draw it and we forget about having to name the longest parent hydrocarbon in the first place. So in this example, the longest chain is a 6-carbon chain that includes those 2 carbon atoms at the top there. If we had started with this methyl group down over here, then we would have ended up with a 5-carbon chain, and that would be incorrect. So we've got a 6-carbon chain, so this is a hexane, and we've got a methyl group at the 3 position, so it's just 3-methylhexane. Okay, here's another example. We've got a 8-carbon chain. We've got methyl groups at the 2 and the 4 position, ethyl group at the 4 position, and a chlorine at the 3 position. So the trick here is to get the alphabetical order right. So chloro starts with a C, that comes in the alphabet before ethyl, starts with an E, and then finally methyl. We don't go for the di, we don't go for the prefix saying how many there are of this. We go for the actual substituent itself, which is methyl. So it's going to be chloro, ethyl, methyl in terms of the ordering. And so it's 3-chloro, 4-ethyl, 2,4-dimethyloctane. Okay, so let's have a look at drawing a couple of compounds here. So we've got 3-ethylpentane. How are we going to draw this? Well, first off, we look at the stem. The pentane bit tells us we need to draw a 5-carbon chain. And then we need to number that. And then at the 3 position in that numbering, we're going to put the ethyl group. So there's our numbering. And now we've got our ethyl group at the 3 position. So the next one, 2,2,4-trimethylpentane. We draw a pentane first. And then we draw in our numbering, 1 through to 5. And we have methyl groups to the 2 position, 2 of them, and 1 at the 4 position. So that we have our trimethylpentane. Okay, so hopefully that helps with naming alkanes that are substituted in a variety of different ways. Thanks for watching.